So the LeetCode problem we are going to solve is called binary tree right side of view. Now we can see that this one is a LeetCode medium problem and also an extremely well-liked problem on LeetCode. The problem statement is actually quite straightforward. We are given the root of a binary tree. Now we need to imagine that as if we are standing on the right side of the binary tree, and then we need to return the values that we see from the right side, and we need to return the top to bottom values. So let's try to understand this problem. Currently we have a binary tree over here. Now imagine yourself that as if you are standing on the right side of the binary tree. So from the right side of the binary tree, you can see only this portion of this given binary tree, which means currently you are only looking at these 4 nodes, and all of because this node is being blocked because of this one, and these 2 nodes are also being blocked because of this one. Okay. So in this case, what is your right side view or your right side vision of this tree? Well, first we need to return the answer in top to bottom manner. So first we are seeing node number 1. Next we are seeing node number 3. Next we are seeing node number 6. And lastly we are seeing node number 7. And this is what we need to return as part of the answer. Now let's first try to understand that what the answer looks like in each of these 3 different scenarios, so we have a clear understanding on what is being expected from our side. So if we take a look at this first tree, well, the answer is going to include, this is going to be the first node, this is going to be the second node, this node would be blocked, so we would not be able to see it, and then once again this node would also be blocked, so we will include this node. So these are the 3 nodes that we are dealing with. Okay. Next, in this particular scenario, we can see that we need to return the right side view. The thing is, hey, there is no node on the right side of the tree. So well, in that case, we can still see the left side of the node as well. So we are going to include this node, and we are also going to include this node in our answer. Okay. And in the lastly, this scenario is slightly tricky. So of course, this node is going to be part of the answer, but then at this particular level, we will have to include this node. Once again, at this particular level, this one is the right child and this one is the left child, but still, because we are standing on the right side, we need to take the value that is closest to us on that particular level. So once again, this node, and then lastly, on this last level, we don't have any particular nodes, so we are going to use this node. Now in each of these 3 scenarios, we can see one very clear distinction in terms of answer. That is, we are seeing that at any given level, we will have to take one node from that particular level. We are going to select the node that is the last node in that particular level. That is the same case for this one, because this is one level, there is only one node. So this is the last node. Over here we have 2 nodes, but we are only going to consider the last node. Once again, we are only going to consider the last node over here as well. This one, there is no explanation needed. This one is slightly trickier example where we can, okay, so this one we understood why we take it. Amongst these 2 nodes, we are closest to this one, so we are taking it. Amongst these 2 nodes, even though these nodes are close to each other, we are once again closest to the right side node, so we are going to take it as part of the answer. And this one once again is still the last node at that particular level. So we are able to establish that for any particular binary tree, the right side of the view is simply going to be doing the level order traversal and finding that what is the last node at that particular level. So in either case, we simply have to do a level order traversal. Now level order traversal for trees typically refers as breadth first search. So we know how to do breadth first search. It's a very common and popular tree traversal techniques. If you don't know what breadth first search is, let me just quickly explain. We are at the root position. So what we are going to do is, for root position, we are going to put it inside a queue. Now we know the property of a queue, that it is a first in, first out type of scenario. For each level, we are going to iterate over all of the children that it has. And if it has the children, we are going to put them on the queue as well. And once again, repeatedly, we are going to keep on subsequently doing the same thing with their children as well. So logically, we would be iterating over in one particular level by level across the entire tree. And that is called breadth first search. So let's try to see our solution in action. So in this case, let me give values to these particular nodes. And we know that the answer in this case is going to be 1, 3, 6, and 7. But currently, let's say that this is our queue. Now in our queue, we are going to keep track of 2 things. Number 1, that what is going to be the last element at any particular node, and number two, that for every single level we will have to keep track of that at what level these particular nodes belong to. Okay, so we can very easily track that, because every time we add a new child, we can just mark it as like a new level that we are adding inside the queue, and apart from that we can simply move forward as it is. So currently the first value is going to be node number 1. For node number 1, because it has children, so we are going to add node number 2 and node number 3 inside our array as well, inside our queue as well. Once again, for both node number 2 and 3, they also have the children of their own. So for node number 2, they have 4 and 5, so we are going to add 4 and 5. For node number 3, they have 6, so we are going to add 6. And lastly, we are going to have value number 7, that is the child of node number 6. So once again, let me just add one more entry over here, 7. So now we can see that I have color coded every single different level based on all the elements for that particular level, and in that particular color coded pattern we need to find the last element. So this is basically going to be by default last element, so we are going to add this to our answer. Next, we have two values at this particular level, so we are going to pop this element out because we don't care. This is the last element, so once again we are going to add that to our answer. Once again, we have 3 elements over here. We are going to pop each one of out, and the moment we reach to the last element, we are also going to mark it as the answer. And then this is also the last element at this particular level, so once again we are going to mark it as the answer, and that's it. This is the whole solution. Now at first glance it looks complicated, but all we are doing is just doing the breadth first search in a common fashion and trying to find the answer. Now in this case, since we are standing on the right side of the binary tree, we are selecting the last element. But same can be said that if we are given a question where we need to find that what is going to be the left side view, where you are standing on the left side of the binary tree, same logic is going to apply. The only thing is now you are going to be dealing with the first entry that pops up inside of your queue for every single new level, and that is what you need to put it in the answer. So basically these are like two questions in just one question by just changing the direction of where you are standing. If you see time complexity in this case, this is going to be big O of n. If you see space complexity, this is also going to be big O of n, because we are using an extra queue to keep track of all the elements that we have iterated so far. Overall, this is like a decent time and space complexity, because this you have to go through this in any of your tree programs unless it's a binary tree and you're trying to search an element. So now let's quickly see the coding solution for this one. Okay, so this is the coding solution. First, we are going to initialize our new array list to store the answer, and we are going to mark it as result. We are also going to check for an edge case that if the given root is equal to null, we can simply return the result. If that is not the case, we are going to initialize our queue, and inside our queue, we are going to populate the very first element, that is going to be the root node. Now we are going to iterate over the tree in the breadth first search manner by stating that while queue is not empty, do this. So first we are going to define that what is the current size of the given queue. Then we are simply going to have a for loop to run over the given queue, where we are going to keep on polling elements at every single position, and we are going to mark the last node of the current level inside the result that we are going to populate. Okay, then we are going to check that for this particular given root value, do we have any left child and do we have any right child? If we do, add the left child and right child to the current queue as well, and this is going to iterate over the entire binary tree in breadth first search manner, and we would have our result array list populated as well. In the end, we can simply return results, and this is the whole solution. So let's try to run the code. Okay, seems like our solution is working as expected. Let's submit this code. And our code runs pretty fast compared to a lot of other solutions. Few things can be improved in terms of space complexity, but anyways, this is a good enough solution. I would be posting this in the GitHub repository that we have created.